I also wanted to do an example on a hypothesis test of a correlation coefficient. A researcher, this is an example of a study in which a hypothesis test of a correlation coefficient would be used. A researcher is wondering if there's a correlation between hours of studying and hours of sleep in the population of college students in the US. If you're wondering whether a correlation exists in a population, you're going to use the hypothesis test of a correlation coefficient. So notice how all of these hypothesis tests are using data from samples to make conclusions about entire populations. But if you're asking a different question about the population, you need a different type of test. Now, instead of asking whether the mean of the population is a certain number, we're asking if there's a correlation in the population. And if we're asking if a certain correlation exists in the population, we need this other type of test. In this type of test, there's two important competing possibilities that need to be considered. The null hypothesis always says that the correlation that you're interested in does not exist in the population. So in this study, the null says there is no correlation between hours of studying and hours of sleep in the US college population. If there is no correlation in the population, what it means is that the population correlation coefficient equals 0. This is a value that actually can't be calculated without data from the entire population. But the null says that it equals 0. The alternative H1 says that the correlation that you're interested in does exist in the population. So in this study, the alternative says there is a correlation between hours of studying and hours of sleep in the US college student population. If there is at least some amount of correlation in the population, meaning if the correlation does exist, then the population correlation coefficient is not 0. That's why I said this here. So the null is the absence of the correlation, the complete absence of the correlation. The alternative is the presence of the correlation. And both of them refer to the entire population that we're studying. Remember that the null and alternative always refer to the entire population and not your specific sample. So now let's look at some possible outcomes. That might be found. If we took a sample from the population let's say that we're taking a sample of 100 people. If we're interested in whether there's a correlation between hours of studying and hours of sleep in our population, that's the data we would have to collect from our sample. We would have to record hours of studying and hours of sleep from our sample members. And based on the answers from these 100 college students, we could look at the correlation inside of the sample to hopefully give us a sense of whether this correlation exists across this entire population. The value that we would calculate for our sample correlation is called R. It measures whether our correlation in our sample is positive or negative and how strong it is. In the center we have 0. Let's make this one 0.20. Which is a little bit of a stronger positive. Let's make this one a 0.40. And let's make this one a 0.60. Let's also look at the same correlations, but now they are negative correlations. Remember that negative point, actually, remember that negative 0.20 is the same strength as positive 0.20, because the strength is the distance from 0. As you go from 0 up to 1, you get stronger positives, and as you go from 0 down to negative 1, you get stronger negatives. Remember that the correlation coefficient can only fall between negative 1 and plus 1. Negative 1 is a perfect negative, and plus 1 is a perfect positive. So these are possible outcomes that we might find with our sample of 100 people when we calculate the sample correlation. Now let's consider the hypothetical possibility in which the null is true and there actually is no correlation in this population. Before we do that, I wanted to talk about why we're using R instead of T. The reason why we're using R is because we're dealing with sample correlations and not sample means. If we were interested in a population mean like we were last time, we would calculate a sample mean and then calculate a t-score based on that. But if we're interested in a population correlation, we take a sample and calculate an R, which is a sample correlation. So when you're dealing with means, it's T, and when you're dealing with correlations, it's R. So the hypothetical situation in which the null is true, and this correlation actually, the correlation between sleep and studying actually does not exist in the college student population. There really is no correlation between studying and sleep in the college student population. And we are, in this situation, we're taking our sample from that population with no correlation in it. Let's think about what outcome we would expect in that situation when our sample really is coming from that population with no correlation in it. Well, if the population correlation coefficient really does equal 0, meaning if there is no correlation in the population, then that automatically means that the population correlation coefficient is 0, because this actually means no correlation in the population. If that is the case, then you expect a sample expect a sample correlation near 0. If the population correlation is 0, you expect a sample correlation near 0. Maybe the sample doesn't have to be exactly 0. It could be end up being a little bit below or a little bit above 0. But if the population does have a correlation of 0, the sample correlation should be somewhere near that, meaning somewhere near 0. And if the population correlation is 0, if the null is true, these outcomes further from 0 are less likely in either direction. So if the population has a 0 correlation, then samples further from 0 are less likely. If the population is 0, you're unlikely to get a strong positive out here or a strong negative down here. You're likely to get something near the center. Now, we can actually calculate a value to actually look at exactly how unlikely these outcomes are getting in the situation of the null being true and there being no correlation in the population. That's done with the p-values. Once again, the p-values always help you look at how unlikely the outcomes are getting in the null situation. So let's look at the correlation of 0.2. If you're dealing with correlations, the df is actually different. It's not n minus 1, it's actually n minus 2. So we had a sample size of 100. df is actually 2 less than that. So enter 98 for a p-value. 0.8419. The opposite would also have to be 0.8419. What about 0.40? Our df hasn't changed because our sample size is still 100. It's 0.69. Let me see if that's actually correct. Looks like that is correct. Now what's 0.69? What's... Oh, sorry, I'm not doing these correctly. I used P from T. We're using P from R because we're dealing with correlations now. So 0.2 and 98. Okay. 0.0460. The opposite is also 0.0460. Now, what I want is to actually find an outcome that has a p-value above 0.05. So maybe I'll put something in here. I'll have a sample where R is correlation is 0.10, which is a really weak positive. And also weak negative of negative 0.10. see what we get here. Point 3222. I told you that the critical values in a hypothesis test are at 0.05, which means our critical correlation coefficient is somewhere between here at 0.05. The positive critical value is in here. The negative critical value is at 0.05, which is between these two. So the positive critical value is somewhere between 0.10 and 0.20. The negative critical value is somewhere between negative 0.10 and negative 0.20. And we have our negative rejection region, just like in the t-test. And we have our negative rejection region up here. Maybe some other time I'll show you how to get the critical correlation coefficients. You actually have to go to a different table than you would for a t-test. So what do these p-values actually mean? It means that if we take a sample of 100 people from a population with no correlation inside of it, and the null is true, if we are taking our sample from that type of population, in that situation, there is a 0.322 chance of getting a correlation in one of these two areas, meaning at least this far from zero. Remember how we have to mark off the outcome and its opposite to create these intervals? What these p-values of these outcomes mean is if we take our sample of 100 from a population with no correlation inside of it, there is a 0.322 chance of reaching either green area. Remember, the p-values are in the null situation. Now, what does this p-value mean? It means that if we take a sample from a population with no correlation inside of it, we have a 0.046 chance of reaching one of these two areas. Which is a smaller chance. So notice how the p-values are dropping when we get further from zero. What that's meaning is if the population has no correlation inside of it, samples with stronger correlations are less and less likely to be found. If the null is true and there's no correlation in the population, then samples with stronger correlations further from zero are less and less likely to be found. If there's no correlation in the population, you're unlikely to get a strong positive or a strong negative. Now, I said that the strong positives and the strong negatives are unlikely to be found if the null is true. But where are actually these strong positives and strong negatives I'm talking about? Um, well, if you go further out here toward the negative rejection region, you're getting stronger. Sorry, I actually didn't do this correctly. I meant to say positive rejection region. You probably noticed that. Going out toward the positive rejection region, you have stronger positive correlations with R's further above 0. When you're going toward the negative rejection region, you're having stronger negative correlations with R correlation coefficients further below 0. So outcomes in the positive rejection region are unlikely if the null is true and there is no correlation in the population. They are more likely if there is a positive correlation in the population. So you're more likely to get one of these stronger positive correlations in your sample if the population actually does have a positive correlation inside of it. These outcomes in the negative rejection region, the stronger negative correlations, are actually unlikely if the null is true and there is no correlation in the population. The strong negative correlations out here, they are more likely if there actually is a negative correlation in the population. So since these outcomes in the positive rejection region are unlikely when the null is true, that means the null is rejected. And they're more likely if there's a positive correlation in the population, which is why in the positive rejection region, you conclude that the population actually does have a positive correlation. These outcomes that are far enough below 0 to be in the negative rejection region are unlikely if the null is true. So they also lead to rejection. And they're also more likely if there's a negative correlation in the population, which is why down here you conclude that there's a negative correlation in the population. So if you get an outcome in the positive rejection region, reject the null of no correlation, conclude that the population has a positive correlation. If you get an outcome in the negative rejection region, reject the null of no correlation and conclude that there is a negative correlation in the population. So I'll write these conclusions down here. Population has a positive correlation. That's a conclusion if you reach the positive rejection region. In the negative rejection region, you have the opposite. If you reach the negative rejection region, you have the opposite conclusion. here I said population has a positive correlation. Down here I said population has a negative correlation. Those are the conclusions you make in these two rejection regions. And if you don't reach either one, then give the null of no correlation the benefit of the doubt, because in this area, the correlation is in the sample is too weak. It's too close to zero. So since it's so weak, you can't be convinced that there actually is a correlation in the entire population. So you're stuck with the null hypothesis. I'll say middle area. What I really mean is when either critical value, this arrow or this arrow, is not reached. I didn't tell you how to find the critical values of the correlation coefficient, but I told you you would have to look in a table